Good day, students. Today we are going to be looking at the pre-calculus exam paper that was written yesterday, the 27th of October, 2022 from the University of Limpopo, and that is UL. And the module code is SMTH000. The paper was very standard. However, I must say that students were beneath their feet, if not biting the dust. Without sounding too technical, let's start this paper from question 2 to 3 as our part 1. And if you are new to the channel, please make sure you subscribe to the channel for the greater disparity and for more mathematics content in Mzansi context. Let's check. We are going to start from question 2 to 3 as our part 1 because the paper was very long. And then question 4 to question 6, it's primarily integral. So I'm going to start with question 2. They are saying that 2.1, evaluate the following limits. They are giving you 3 limits, and all of them are 4 marks. And then let's check how are we going to go about it. The first one is the limit as x approaches 3 of the square root of x squared plus 7 minus 4 over x squared minus 3x. So I'm going to do it on a new paper here to say that is my question 2. This is where we are going to be starting. It's our part 1. You must also watch part 2 where I'll be doing integrals and derivatives. Extremely easy in them. So 2.1, we want to find the limits, and then we are given 2.1.1, and that is the limit as x goes to positive 3. Let's check again. That is root of x squared plus 7 minus 4 over x squared minus 3x. So I'm going to copy that here to say that is the square root of x squared plus 7 minus 4 divided by x squared minus 3x. Let's check. This is limits. So when dealing with limits, the first thing we're going to do is we are going to take this approach and substitute it in a position of x and see what do we get. Let's check. If we get a value, then it's our bonus. 3 squared is going to be 9 plus 7. It gives you 16 under the square root. That is 4 minus 4. So that is going to give you 0 over. If you put a 3 here, it's going to also give you 0 over 0. So this limit, it means that you can use L'Hopital's rule or you can rationalize, or you can use other techniques because I see that there is a square root here. So the first thing to do would be to rationalize, or you can use your L'Hopital's rule. The answer will still be the same. But I'm going to rationalize here to say that let me remove that square root, and that is going to be equals to the limit as x goes to positive 3. And then I copy the same problem. That is really this one here. And then I need to rationalize that. So I remove the numerator. That is really going to be x squared plus 7 and then plus 4 divided by the square root of x squared plus 7 plus positive 4. And if you try to do it nicely, you'll see that you are going to get the following. Check. In the numerator, if you multiply this situation here, and this situation is going to be x squared plus 7 and then minus 16. So I'm going to just write this line here that I'm going to get, first thing first, I'm going to get x squared plus 7 minus 16. I also have x squared minus 3x. This is x squared into the square root of x squared plus 7 plus positive 4 there. You can really reduce this one a bit, and then you close that. So what I'm going to do is I'm going to say to myself, this is x goes to positive 3. I don't know why I'm writing 0. I'm used to the limits approaching 0. So that should be 3. You're going to approach positive 3 just right there. And then in the numerator, if you try to simplify this stuff, that is going to be 7 minus 16, and that is 9. So you are left with x squared minus 9. And then if you want to do that nicely, that is going to be x minus 3 into x plus positive 3. It's the same as x squared minus 9 is this one. We call it a difference of two squares. So you're going to divide this stuff by this one. You can see that you can factor out your x for this factor here. That is going to be, hey, my thing is misbehaving now. This is going to be x into, you'll be left with x minus 3. And then now you have the square root of x squared plus 7 plus positive 4 there. And then now you just need to simplify where you can. That is going to be the limit as x goes to positive 3. Observe that this factor and this factor, they are going to undo each other. And then now you are going to be left with x plus positive 3. You divide this stuff by x just right there. And then the other factor now is the square root of x squared plus positive 7 plus 4. Now you just need to substitute the value of the limit and see what do you get after simplifying that stuff. So that is really going to be 3 plus 3 divided by, you take that 3 and put it there. That is going to be 3 into, it's going to be 3 squared plus 7 plus 4. What I'm doing now is to substitute the value of the limit. And that should really ties down to 6 divided by 3 into this stuff here is going to be 16 under the square root. So it's going to be plus 4, the other 4 here. And then you simplify it nicely. You'll see that this is going to be 6 over 3 into 8. And if you have got the brain power, you can see that this is going to take away that 3. So you'll be left with 2. So 2 over 8. 2 over 8 is primarily 1 over 4, which is also known as a quarter. So that should be the answer for that particular limit, the first limit. It should be very easy. I hope you got that 4 marks. You could have used your L'Hopital's rule, or you could have used other methods, So here I just rationalized to remove the square root. I think it's the best approach when dealing with limits. Now, let's check the next question. What are they saying there? They are saying that this is the limit as x goes to negative infinity of the square root of 1 plus x squared over 2x plus 3. Okay, so let's attend it. So that is 2.1.2. We are having the limit approaching negative infinity of what? Of the square root. So this is 1 plus x squared divided by your 2x and then a plus 3. So we want to do this limit. Notice that we are now approaching infinity. So this is where you largely deal with taking out the highest degree in a polynomial or inside the square root. So in this particular case, we see that we have a square root. So I'm going to focus on that stuff. That is the limit as x goes to negative infinity of the square root. I can take out my x squared inside, and then I'll be left with 1 over x squared plus 1 divided by, this is 2x, and then a plus 3. Notice that this will boil down to the limit as x goes to negative infinity. If you try to simplify this particular stuff here, I hope you know how to simplify this situation. It's a very easy polynomial stuff. You square this one, it's really going to give you x, and then now you square the other factor, and that is the square root of 1 over x squared plus 1. What we are using here is this rule from the lower grades. it states that if you have the square root of AB being multiplying each other, it's the same as the square root of A multiplied by the square root of B. It's what I'm using in there. So this should be very easy to say. Now you're going to divide this by 2x plus 1. So I'm going to do the same stuff and take the highest degree in my denominator, and then I'm left now with a 2 plus 3 over x. That should be very easy to you guys. Let's check. So you're going to get the limit as x goes to negative infinity. Observe that these two guys here, they really undo each other, or they cancel. So you are primarily left with the square root of 1 over x squared plus 1 divided by 2 plus 3 over x. So what can you do now? Now you can try to substitute your infinity for x. Notice that if you do that, you are going to put infinity here, negative infinity, by the way. So it's going to be 0 plus 1 there, divided by 2 plus 3 over negative infinity. We do not have a negative 0, so it's positive 0. Please, guys, get that stuff carefully. So you are primarily going to get 1 over 2 in there. When you square 0 plus 1, it's going to be 1. And then 2 plus 0, it's primarily a 2. So the answer, you can see that it ties down to a positive half. So this is how you'll go about this particular problem. Let's see the next question on limit 2.1.3. The limit as x goes to 0 of the tangent of x minus x over x cubed. I hope it's visible, because I got this paper from some students, and some I couldn't really see some of the questions. So this is 2.1.3, and then we have the limit as x goes to 0 of the tangent of x minus x divided by x cubed. So if you want to think of factorization, a whole range of stuff that you did before L'Hopital's rule, here it's not going to work. So you are bound to use the L'Hopital's rule on the basis that if you take this 0 for x and plug it here, tan 0 is really going to give you 0, minus 0 is 0, and 0 cubed is 0, it's primarily 0. So you're going to get a 0 over 0 just right there. That means you are going to apply your L'Hopital's rule. Check. You are going to have a limit as x goes to 0 of the derivative of the numerator. If you derive tangent, you get a secant squared of x. You derive x is primarily 1. You divide the stuff by the derivative of x cubed. That's ordinary functions, and you get 3x squared. All right. So you do the same stuff. You take 0 and plug it here. So sec squared of 0, it's primarily a 1. Think about it. Sec squared is the same as 1 over cos squared. But cos 0 is 1. So this is 1 minus 1 there. So that is really 0 primarily. So obviously it's going to be 0 as well. So you're going to get a 0 over 0 again. So that means it is L'Hopital's rule. You must drive it. So to do that, we are going to differentiate again. That is the limit as x goes to 0. If you derive a secant squared of x, is the chain rule. You're going to get a 2 sec x times the derivative of sec x, which is sec x times tangent. So it's primarily going to be 2 sec squared of x multiplied by the tangent in there, divided by, this is going to be, when you derive 1, it's 0. So this derivative is going to give you this one. And then you derive 3x squared, that is primarily 6x. It's ordinary functions. you do the same stuff. You take 0 there and put it in a position of x. So this is going to be 1 times 2. But when you put 0 there for the tangent, it's going to be 0. So it demystifies the whole thing to be 0. And then if you put a 0 there, it's clear that it's going to be 0. So this is really 0 over 0 again. That means you must drive for the third time. So let's do that. But before you even do that, you can see that this 2 is going to cancel with that. You know, it's really going to cancel with that. So you can say to yourself, now let me just write the limit as x goes to 0 of a secant squared of x multiplied by the tangent of x divided by 3x. If you simplify those 2 and your 6 there. So you want to drive, I hope it's the last time, you want to drive the numerator. If you differentiate this one, you're going to use the product rule, because these are two functions multiplying each other, so it's a product rule. How are you going to do that? That should be, let's check. You differentiate this one, which is this one right here. It's the one that we got primarily. So if you drive it, you are going to get this one, and then you keep your tangent. So you are going to get, let's check. If you derive this, multiply by that one. I'm trying to do everything in the head, but it's fine. Let me do it in this way. That if I derive sec, it's something which we know the answer of. Okay, let me just write everything. This is going to be 2 sec squared of x, and then a times the tangent of x. I have to keep, let me just do this. I have to keep the tangent now. So this is going to be tangent, so it's going to be tan squared. Basically, it's what I was trying to do. And then a plus, if now you keep the secant, and then you differentiate the tangent, you're going to get a secant squared of x. If you derive this one, this is really going to be 3. You know, this is really going to be 3. Let's check. What are we going to get? We are going to get the limit as x goes to 0. This demystified to 2 sec squared of x multiplied by the tangent squared of x plus that stuff. It's primarily a secant to the power 4 of x divided by, let's check, that is divided by 3. Now let's plug our 0 and see what we get. You say to yourself, when x is 0, this is going to be 1, and then this is going to be 0. And then now secant to the power 4, sec of 0 is 1, 1 to the power 4, it's primarily 1. So you're going to get a 0 for this term because this one is 0. So it's going to be 0 plus 1 divided by 3, and the answer should really give you 1/3 as the answer. So this should be the answer for that particular problem. Yeah, it was really doable. I hope you guys see how I'm doing it, and please don't forget to comment if it challenged you or if you are in disagreement to what I'm writing. But I believe you are in agreement of what I'm writing. So this is the end of question 2.1. We are going to look at 2.2, which is primarily this one. They are now saying state the formal definition of a limit. So you want to state the formal definition of a limit. So that is your really definitions that I presume that you guys know how to state. It's really easy. I'm going to state it for you. Okay, So we are now in 2.2. We want to state that stuff. It states that suppose that the function f is defined near a point, and that point, let's call it C. When we say a function is defined near a point, we are primarily saying that that is, let me just write e.g. in a neighborhood. So I'm going to write in a neighborhood of a point C, C there. Then the limit as x goes to that point C there, this particular point C of the function f at x equaling to L. Let me say this is going to be true. This is going to be true if and only if, you must write if and only if for every epsilon bigger than 0, there exists a delta bigger than 0, and then such that the distance between these two numbers, that is x and c, the distance between these two guys here, that is x and c, so it's primarily positive, hence we are using the modulus. That is going to be bigger than 0, but it's going to be less than the delta there. And then now the distance between the function itself and the limit value there, that is your f at x minus L there, that is going to be less than the epsilon. So this is how you will state that. However, if there is another way of stating it, and you can do that, it's still fine. But this is the formal definition of a limit. You are primarily dealing with the delta and the epsilon in there. It's really easy, eh? So we are going to answer the next question. What are they saying? That's how you're going to state it, by the way. It's primarily easy. Now they are saying use the formal definition of a limit to show that the limit as x goes to -3 of the absolute value of x plus 4, which is the modulus of x plus 4, is equals to 1. So we are going to be using the definitions of limit to be proving that stuff. So we get 2.3. We must prove that the limit as x goes to -3 of the absolute value of x plus 4 is going to give us a value of 1. So when they say use the formal definition of limits, you are primarily going to use this stuff just right here. All right, so this is really easy. I don't want to lie. So you are going to say to yourself now, solution. You say given any epsilon bigger than 0, or you can say for each epsilon bigger than 0, or for every epsilon bigger than 0, there exists a delta bigger than 0, such that the distance between these two guys, so that is the distance between x and 3, so it's going to become positive. If you say x minus 3, that should be bigger than 0, but less than the delta there. And then Then now the distance between the functions, let me just put it here. Then now the distance between the function, which is the modulus right now, which is the modulus of x plus 4, like that, that distance minus, in fact, the distance between this function and the limit value there, that is your 1. So I'm going to put a 1 there and really close that and say that must give us something which is going to be less than epsilon. So this is very easy, I presuppose. So now you are going to compare this one and that one. In most cases than not, you are going to be proving that this stuff is going to give you somehow, somewhere, the absolute value of x plus 3. So that should be very easy, I must say. So I'm going to then say, now, let me consider this particular situation here. And that is the absolute value of the modulus of x plus 4 minus 1 there, that is less than the epsilon. Think about it. If now you want to apply the properties of modulus, that is going to be a reverse triangle of inequality. That is the modulus of x plus 4. It's going to give you the modulus of x plus 4 minus, which is this minus the modulus of 1. That is going to give you the absolute value of 1 less than the epsilon. But check something. This stuff is going to be less or equals to this one here. This particular value here. And that is going to be less than the epsilon, which is primarily this particular situation. On the premise of the fact that this is going to be a positive, and this may be somehow, somewhere be a negative, hence we are saying that it must be less or equals to this particular situation in there. So because these guys really here are less than the epsilon, you can then now say, well, let me work with this one because it is the simplified version of that one. And that is going to be the absolute value of x plus 4 minus the absolute value of 1. That is still less than the epsilon in there. Now, pay attention. This becomes the absolute value of x plus 4 minus modulus of 1. It's going to give you 1 less than the epsilon. Now you can transpose your 1 that side. You are going to get x plus 4. That is going to be less than the epsilon plus 1. Check something. We are dealing with modulus here. If you have the absolute value of x less than, say, maybe a, this is the same as saying negative a is less than what is inside the modulus and less than the positive of itself, which is basically what we are seeing here. This means that if I'm to apply this rule here in this particular problem, I'm going to get the negative of this situation, and that is epsilon plus 1 is less than what is inside the modulus, and that is x plus 4 less than the positive of this stuff, that is epsilon plus 1. So now you'll see that from here it's a basic algebra. That is to say it's negative epsilon and then a plus, it's going to be negative 1 less than your x plus for the less than epsilon plus 1. All right. So you'll see that you want to get x plus 3. Like I said, you need to get x plus 3. So what can you do with this equation? If you want to get x plus 3 in here, what can you do? If you want to get x plus 3 there, think about it. You're going to subtract 1 from both sides of the equation. You're going to arrive to x plus 3 there. So let me subtract 1 from both sides of the equation. And let's see what we are going to get in there. if I subtract 1, I'm going to get minus epsilon. This minus 1 is going to be negative 2, less than x plus, this is going to be 3, what I'm looking for, and that is going to be less than the epsilon. If you subtract 1 from that, you're going to get epsilon. This is going to become 0 if you subtract 1. So notice that this value here, this particular value here, must be the positive on the right side of it in order for this equation to be true. So I'm going to say to myself, therefore, I'm going to get the negative epsilon minus 2 less than x plus 3 less than the epsilon, which is this one. So this epsilon is something which is bigger than 0, but it has to be less than now epsilon plus 2. Where am I getting this one? This is the negation of this particular situation. Notice that this is the epsilon plus 2. So it's something bigger than 0 plus 2. So it's always going to be bigger than the epsilon. Hence, the epsilon is less than this situation there. And then now you can say to yourself that this is negative epsilon minus 2 in between x plus 3. We can now take that inequality, which is going to be epsilon plus 2. Now, so now you need to convert, you are now here, you must take it back to that one. So now this means to you that this particular stuff is the same as the absolute value of x plus 3 less than the positive of that stuff, and that is epsilon plus 2. Think about it. If you expand this, you are going to get back this particular line here. So you are converting back this one to its modulus. All right, and that should be very easy. And I said to you, if you can get this one from what you're comparing it with, which is this one, if you can get that from this one, then that then gives you your delta. That then gives you your delta to say, therefore, the answer that they are looking for, its delta is going to be equals to that one, which is epsilon plus 2. So that should really suffice to that particular answer there. I hope you get the logic behind this one. Yeah, it was really a game of a cat and a mouse. You can see that it was a long walk in the park, but we finally arrived to our destiny. Hence, I'm doing this paper in part so that I also rest. That was 2.3. We are given 2.4 now. They are saying to you that let f at x, yeah, I think they made a mistake here. That should be f at x, I believe. So I hope they gave it to you that in class or in the exam room, that should be f. I didn't really see that, so that should be f at x. Okay, let's assume that is f at x. It has to be f at x. You can see that this is piecewise function, so it has to be f at x there. Let's hope they told you in class, because here they are talking about it, you see. I hope in class it was corrected, or in the exam room. So let f at x be equals to 1 over x, where x is less or equals to negative 1. And then x minus 1 over 2 is in between minus 1 and 1 exclusive. And the square root of x is bigger than positive 1. Determine whether or not the function is continuous at those points. And that is x is equal to negative 1 and then x is equal to positive 1. So that should really be very easy. Let's see. That is 2.4. That is 2.4. We are given f at x, it's a piecewise function. Well, we are told that 1 over x, it's really less than or equals to negative 1. And then x minus 1 over 2, that they are saying that x here, it's in between negative 1 and 1 exclusive. And then the other one is the radicand of x. that is primarily x bigger than 1 there. So we want to check the continuity at a certain points. So that is 2.4.1. Check the continuity at -1. And then 2.4.2 is primarily at +1. So this should really be very easy, guys. How will you do it? Well, if we talk about continuity, we are saying that f at -1, first thing first, should really be defined in the domain, and those are your domain. So that is really going to be equals to the limit as x goes to -1 of the function itself. That must really be true. So you must check that if it's really true. So I'm going to say to myself now, let me find f at -1. Which function am I going to take? I'm going to take this function because that's where f at -1 is defined there. All right. So that is really going to be 1 over x, which really give me 1 over -1, and that is -1. So I want to find the limit as x goes to -1 from both sides, that is left and right. So let me find the limit as x goes to -1 from the left of f at x. I'm going to choose the same function because it's going to approach -1 from the left. And that is the limit as x goes to -1 of 1 over x. And the answer is going to be -1. I'm now going to take the limit as x goes to -1 from the right of it. And I'm going to check where x is bigger than -1. So x is bigger than -1 in this region. So that means I'm going to take this function, So that is going to be x minus 1 over 2. If you plug -1 there, you're going to get -1 over 2, and you get -1 as the answer there. So you can see that the limit does exist, So the limit as x goes to -1 of f at x is equals to -1. The limit does exist in actual fact. You can also say since the limit as x goes to -1 from the left of f is equals to the limit as x goes to -1 from the right of f, and they are both equals to -1. So it means that the limit as x goes to -1 itself from both sides, they are really equal, and the limit does exist. And f at -1, you got -1 as well. So therefore, this conclude that f at -1 equals to the limit as x goes to -1 of f at x, which is basically this condition which we're trying to check if it is true. So it is true because they are all equals to -1 there. This is really true. You managed to prove that, you saw. So this will then mean that f is continuous. So f is continuous at that particular point, at x is equals to -1. So here f at x is continuous at this particular point because f at -1 is defined, and it is also equals to the limit as x goes to -1 of f at x at that particular point. So let's check the next one. That is 2.4. That should be 2 there. All right. So they are saying there that was x is equals to +1. That was x is equals to +1. Let me confirm that again. So that is really a +1. Yeah, this paper was very long. Okay. So we get +1 there. So the same stuff that we've been doing, we are going to be doing it even here. So here we are going to test the f at 1 if it is defined, and it must equals to the limit as x goes to 1 of f at x. So let's check if this is true. Let's check. Well, we are going to first test f at 1. Which function are we going to take for f at 1? Where is 1 defined in this interval? 1 is defined in this particular interval, this last one. Remember that they gave it to you just right here, that this is x bigger than or equals to 1. So that was inclusive, that particular one. So I'm now then going to say that let me find, using the square root of x, the last function, f at 1. So that is really going to give me root 1, and the answer will be 1. And I need to find the limit as x goes to 1 from the left of f at x, which is going to be the limit as x goes to 1 of f. You choose your f. So this is going to be approaching from the left. X is less than 1 there. So you're going to be saying this is x minus 1 over 2. And if you plug 1 there, you are going to get a 0 as a limit there. Now you go to the right. So of f at x, that is going to be the limit as x goes to 1 from the right. So the right is equals to f at a point is this one. That is root x. That is your root of x. And if you plug 1 there, you get 1. So this tells you that the limit as x goes to 1 from the left of f at x is not equals to the limit as x goes to 1 from the right of f at x. They are not equal. And then this concludes to you that the limit as x goes to 1 of f at x does not exist. The limit there as x goes to 1 of f at x does not exist. So as a conclusion, f at 1 there is not equals to the limit as x goes to 1 of f at x. So if this equation is not true, it says that f is not continuous. F is not continuous at x is equals to 1. So this is how you would go about the continuity at those points. There was -1 and +1. What is the last question? Okay, that was the last question, eh? In question 2, yeah, that summarized question 2. So we are going to be looking at question 3 now. I think it will be the last question. Question 4 and question 5 and 6, I'm going to do it as soon as I'm done uploading this one as part 1. And then multiple choice, I will do that as part 3. I want us to work this whole thing. What are they saying in question 3? I didn't really see that. Use the definition of a derivative to find f prime at x if f at x equals to sine x. Okay, so we want to find the derivative. So let's write question 3. We want to find f prime at x if f at x is equals to sine x. But we must use the definition of limits. That is the first principle. So we're going to get f prime at x is equals to the limit as h tend to 0 of what? Of f of x plus h minus f of x. that is going to be divided by h. That is your first principle. You know it from high school. It's the meaning of a definition of derivatives there. That is really going to give you the limit as h tend to 0 of sine of x plus h minus sine x there divided by h. And you will see that this is going to give you the limit as h tend to 0, everything divided by h. But think about it, what is this one? That is the compound angle of identities from grade 12, and that becomes sine x cos x plus, this becomes cos x now, and then sine h minus sine x. So I'm going to write minus sine x, which is really that one there. So that should really be very easy, guys. Very, very, very easy. So I'm going to group the like terms. What are my like terms? My like terms is primarily this one and this one there. They must be grouped together because they have the sine x there. And that is going to be the limit as h tend to 0. Let's check. That is going to be h. And if you group sine x cos h minus sine x there, and then you are left now with plus cos x sine h, and then let's check in the numerator. What are you going to do there? This is still divided by h. Check something here. This is still your h, and then you can take out your sine x there. That becomes sine of x, and you'll be left with cos h minus 1 there, and then plus this one, this term here. So I may need to really put it there and divide this by h. We are almost done. So we are going to say that is, let me just do this. That is my function. Let's check. What do we get? We get the limit as h tend to 0. What is that? That is the same as saying this part here, this one, divided by h plus this particular term there. And then I'm going to get this one, and that is going to be divided by h. It's the same stuff. Then now I'm going to take the limit of the sum. So already you can see that this is a constant because you are approaching its h. It's a function of h. So anything of x is going to be a constant. You're going to have a sine x as a constant. And then now you're going to get the limit as h tend to 0 of cos h minus 1 over h, and then plus anything that is having x, it really becomes a constant, and it can be taken out as a constant. I'm just going to put it here, and then now I evaluate the remaining stuff. That's the limit as x goes to sine h over h. You'll see that let me try to reduce that for more space there. Now we're going to get sine x into that limit. So that is going to take you back to trig limits, and that is going to give you 0 plus cos x. This in trig limits is going to give you 1, or you can still use L'Hopital's rule. You still get 1 and you still get a 0 there. But these are trig limits. You use trig limits rules, and this will really give you 0 times sine x is primarily 0 plus cos x times 1. So that is going to give you cos x. As a result, you're going to get cos x. So the derivative of sine x should really give you a cos x from the first principle. That is really easy, I don't want to lie. But if you are practicing, that should really be very easy, I must say. All right. And then let's check the next question. And then that is 3.2. What are they saying then? Let's check 3.2. Yeah, we've been doing these things. So 3.2. Use the quotient rule to find the y prime if y equals to 5x over and the square root of x squared over the square root of x minus 2x squared. Okay, so let's find the y prime there. So we're given y equals to 5x over the square root of x minus 2x squared. We want to find a y prime there. Let's find it. So this is really easy. We'll say y prime is equals to, we're going to use quotient rule, like as per the guideline. We're going to square this one. It's our denominator. We're going to square that and derive 5x. So it's going to give us 5. And then we keep this other one. We keep our g. So that is going to be x minus 2x squared. And then what now? Minus. We keep our numerator. That is 5x. Now we are going to multiply by the derivative of our denominator. If you derive that with the quotient rule, we are applying quotient rule, but this derivative is it's primarily a chain rule, eh? So I'm going to use a chain rule there, and that is to say it's 1 over 2. That is 1 over 2 into x minus 2x squared to the power negative 1 over 2. Let me enlarge this line, and then multiply by the derivative of what is inside. So you get 1 primarily minus 4x. That is the derivative of what is inside. You can always close that. And if you want to simplify this, you will see that you are going to have 5, the square root of that is going to be the square root of what now? Of x minus 2x squared. And then this is really going to be minus 5x over 2 into 1 minus 4x multiplied by that stuff. That is primarily 1 minus 2x squared to the power negative 1 over 2. I wanted to check if I can really play with that and put as positive exponents. It's going to be 1 over the square root of that stuff. Okay, let's do it. So that is going to be multiplied by 1 over the square root of x minus 2x squared. It's the same as this particular factor here, but this one and this one are going to undo each other, and you'll be left with x minus 2x squared. It's what you are going to be having. Well, let's check if you can simplify further. So this is 5, and then this is 5 into x minus 2x squared to the power 1 over 2 divided by x minus 2 x squared, and then minus this is going to be 5x into 1 minus 4x divided by 2, the square root of x minus 2x squared divided by x minus 2x squared. So you can see that You can still simplify because this is raised by 1. So the base are the same. You can subtract 1 from half there. And then half minus 1, it's primarily a negative half. So you are going to get a 5. If it's a negative half, you're going to get a 5 over the square root of x minus 2x squared minus, let's just do it in this way, that this is going to be 5x into 1 minus 4x divided by 2 into x minus 2x squared to the power 1 over 2 multiplied by the inv10 of this. So that is going to be the reciprocal of this one. It's going to be 1 over that one. So it's going to be 1 over 1 minus 2x squared to the power 1, like that. So this will suffice to 5 over the square root of x minus 2x squared minus 5x into 1 minus 4x divided by the multiplication of that. So this is going to be 2 into x minus 2x squared to the power 1 plus half is 3 over 2. Yeah, this is the simplified answer of it, but normally your answer should really end here, unless if they say simplify or prove, this is what you must write. But I was trying to exercise my mind by simplifying the answer. So it's really going to boil down to this one. And that was 3.2. We are going to look at 5.3. Let's check 5.3. 3.3. I don't know why I keep saying that. Okay, that is 3.3 there. Use the logarithmic differentiation to find y prime if y equals to 5x plus 8, the square root, multiplied by the cube roots of 1 minus 9 cos 4x over the fourth roots of x squared plus 10x. Okay. We want to use the logarithmic derivative to do that. So we are going to get y equals to the square root of, that was 5x plus 8 multiplied by the cube roots. The cube roots there of 1 minus 9 cos of 4x divided by the fourth roots divided by the fourth roots. Okay, so the fourth root is primarily x squared plus 10x, so that is 4. We want to use the logarithmic derivative. That means we must simplify this through or by means of natural log. So I'm going to take the natural log both sides. I'm going to write solution. The natural log both sides of y is going to be the natural log of that stuff here. So I'm going to take that natural log. Let's see what we're going to get if we try to simplify this. So this will boil down to, remember here is natural log. And then you are going to get the natural log of this factor here. That is primarily 5x plus 8 to the power 1 over 2 plus the natural log of 1 minus 9 cos of 4x to the power 1 over 3, the cube root of that, and then a minus now the one for the denominator, It's going to be a natural log of x squared plus 10x to the power 1 over 4. I hope you know how to simplify that natural log there. This one, it's primarily easy there. We use rules of natural logs. And as a result, you'll see that you'll get a natural log of y equaling to, this will be 1 over 2, a natural log of 5x plus 8 plus 1 over 3, the natural log of 1 minus 9 cos of 4x minus 1 over 4, the natural log of x squared plus 10x there. Well, and you now need to take some derivatives there, both sides. That should be very easy. Let's derive in y now. That is going to be y prime over y. If you differentiate that, that should be very easy as well. It's going to give you 5 divided by 2 into 5x plus 8. And then let's check plus this derivative. It's going to be 36, I guess. That should be positive 36. And then a sine of 4x divided by 3 into 1 minus a cos of 4x. Be very careful there. Minus, this should give us a 2x plus 10 divided by 4 into x squared, and then plus 10x. So you are looking for y prime. You're going to multiply this whole stuff by y. So y prime becomes y into, you multiply this whole thing there by your y, I'm just going to really close that. But check something. What is your y? Your y was given just right here. So you need to really substitute your y back with this particular answer here. Yeah, this paper was misbehaving. So you then now say, therefore, my y prime is going to be equals to this stuff, this particular stuff here. Let me just copy it. So that is y. I'm just gonna plug it. Remember, this was y. So I'm just going to reduce because I need to multiply it by this one. Remember, this is y, which is this one there. You multiply this by this whole stuff there. So I'm just gonna really plug it here, but let me reduce it so that I can really put it nicely there. Cool. So I'm gonna close that and really make it one color. Let's give it a visible one. I don't know. Yeah. I hope that is really visible enough. Let's just have that stuff. Cool. And really make it bigger so that you guys can see. Yeah, that should be the final answer of that particular derivative. Yeah, it was worth the struggle. This is how you will have found that particular derivative. I must say that you guys were really battling with your last breath. Yeah, this is how you go about it. And if you have any question, don't forget to comment here. I will do also the issue of the integrals as part 2, and that stuff of the concave down and concave up. Well, let me just do that. I look at the last question of question 3. show that d squared y over dx squared is equals to negative 2 over y cubed. Okay, we need to prove that, and we're given the circle. That is x squared plus y squared is equals to 2. Okay. 3.4, we want to show that d squared y over dx squared is equals to negative 2 over, is it y cubed? And we're given that the circle is y squared plus x squared plus y squared is equals to 2. So I'm going to drive that circle. Let's differentiate that circle. You drive x squared, you get 2x, plus you drive your y, you get 2y multiplied by a y prime there, which is the first derivative rather. dy by dx is equals to the derivative of 2. That should suffice to what? Should be 0 if you drive a constant. You want to solve for dy. So this will be 2y dy by dx is equals to negative 2x. And this should really be dy by dx is equals to, you divide both sides by 2y. So this will be 2y over 2x, negative 2x over 2y. And as a result, you are going to arrive to 2y by, dx by dy by dx is equals to negative x over y. That is the first derivative. You want to get the second derivative. That means you're going to differentiate that, and you get d squared y over dx squared. It's the second derivative of that stuff. And this should be, I'm going to take this negative out and really drive this one. That should really be y squared. You drive the numerator, it's primarily 1. You keep your denominator, so it's 1 times y, which is y, minus you keep your x, drive the denominator, that is going to be y prime. You close that, and you get a negative of y, and then minus x. So that is x times the y prime. This is the y prime, this is the y prime. So the y prime, you guys got negative x over y. You close that, this is over y squared. You can always close it and simplify it. That is y minus, it becomes positive now, x squared over y divided by y squared. So you need to simplify this maths. So this is negative. In the numerator, let's simplify the numerator. That becomes y, and that becomes what now? That becomes y squared, and then a plus x squared. This whole stuff is divided by y squared, just like that. And then notice that this will give you a negative of this stuff. I want to simplify this one there, and then divided by y squared, which is primarily the same as now saying it's multiplied by 1 over y squared. I hope you know this logic. Well, as a result, you get negative of x squared plus y squared divided by y cubed. This one is the simplified version. But check something here. But you are given something that x squared plus y squared is equals to 2. So you're going to say that x squared plus y squared was given as 2. So this one then ties down to dy by dx, but that is your second derivative. That is going to be equals to the negative, which is this negative there, multiplying this whole stuff, And you see that this is going to give you 2 from this equation. And that is 2 divided by y cubed. So this is how you really prove that last question. It's primarily easy, eh? It's really easy. So you can really go and check those things. So you had to prove that d squared y over dx squared is equals to minus 2 over y cubed if that circle was equated to 2 there. So yeah, this is how I would go about it. And then question 4 and question 6, I'll do that as part 3. Thank you very much for watching.